problems to check the stability condition for an LTI system. Okay, so the first one is so the question is, which of the following impulse responses corresponds to stable LTI system? Let us take the first one. The first one is h1 of t is equal to e to the minus 1 minus 2j times t into times of u of t. Now to find the stability, put the values from minus infinity to plus infinity for t. That is one way of doing. Substitute t from minus infinity to plus infinity. Okay. Now h1 of minus infinity, what will you get? You will get, first of all, you rewrite this function, or you can write away minus of 1 minus 2j times infinity and u of minus infinity. By the way, what is u of minus infinity? 0. Okay, and so 0 into anything, it is 0. Okay, it gives finite value. And now substitute t is equal to infinity, then h1 of plus infinity, which is e to the minus of 1 minus 2j times infinity, u of infinity. What is u of infinity? It is equal to 1. Now infinity times minus e to the minus infinity, it is becoming 0. So still, if you want to write very clearly, then e to the minus 1, let me write down h1 of t is equal to e to the minus t times e to the j2t times u of t, right? Like that I can write. Okay, so h1 of infinity is equal to e to the minus infinity times e to the j times 2 infinity times u of infinity. This is equal to 1, fine, understood, and this one is equal to 0, fine. What about this guy? E to the j times 2 infinity. I can write infinity times anything is infinity other than 0. So let me write e to the j infinity. So we know the formula, cos of infinity plus or minus, no, it is plus, so you only put plus, j times sine infinity. What is cos infinity? Whatever the argument you put here, it doesn't matter whether you put infinity or 0 or whatever it is an oscillating function, right? It keep on oscillates. It oscillates between plus 1 and minus 1. So therefore this always gives finite value, and sine also gives always finite value. So this is going to be a finite number, right? Therefore your h of infinity is equal to 0 times a finite number times 1. So this is going to be 0. So if we substitute all range of values, it is going to be a finite value. So for all time the system produces stable output. So the system is stable, or you can test the absolutely integrable. Okay, absolutely integrable, that's what we discussed in the previous lecture, right? So what we mean by absolutely integrable, like integral of h of tau d tau from minus infinity to plus infinity is equal to, it should be less than infinity, that's what we said. Okay, now what h of t is given, h of t is equal to e to the minus t times e to the j times 2t u of t. This is what is given. What is h of tau? E to the minus tau e to the j2 tau u of tau. No need of tau also, you can straight away substitute here, but we need the result in the time domain, so let us keep it as it is, no problem. So since u of tau let me write down as it is, no problem. E to the minus tau, e to the j2 tau, u of tau, take magnitude d tau. Now e to the minus infinity plus infinity, e to the minus tau magnitude, e to the j2 tau magnitude, u of tau magnitude d tau. What is u of tau? U of tau is equal to 1 for tau greater than or equal to 0. Therefore, the integral is from now 0 to infinity. For tau less than 0, the integration becomes 0. So, still if you want, you can put minus infinity to 0, e to the minus tau. What about this guy? That guy becomes 1. And u of tau d tau plus 0 to infinity, e to the minus tau 1 times u of tau d tau. Now from minus infinity to 0, what is the u of tau value? It is equal to 0. Therefore, this is 0. So the first integration leads to 0 and the second part is survives. Second part survives. So therefore 0 to infinity, e to the minus tau d tau. So e to the minus tau divided by minus 1, the limit is 0 to infinity. Now what is upper limit? E to the minus infinite minus lower limit, e to the 0 divided by minus 1. So it is 1. So 1 is less than infinity. So this is absolutely integrable. So this A is a stable system, a stable LTI system. Okay. Now let us take the second part, second problem. H2 of t is equal to e to the minus t cos 2t times u of t. Now again, if you recall, like integral of h2 of t absolutely square integrable, that is the absolutely integrable, minus infinity to plus infinity. Okay, so substitute e to the minus t cos of 2t, then dt. You can put tau also, no problem. After all, t or tau, it's a dummy variable in this calculation. It's not mandatory to put only tau. Minus infinity to plus infinity. Now this integral is finite valued. I'm sorry, I forgot to substitute the value. U of t dt. Now this is, I can write as 0 to infinity e to the minus t cos of 2t and dt, and this is absolutely integrable. Why? Why is it absolutely integrable? Because if you plot the function, as we know, e power minus t goes like this, and with that, it as time progresses, it is decaying exponential. It is decaying exponential. When you integrate decaying exponential, the area is finite. Area is finite, right? And you are multiplying with the cos 2t, and the maximum value of cos 2t is 1, and the minimum value of cos 2t is minus 1. That means you are not taking cos 2t as it is, you are taking the magnitude of cos 2t like this. Now the maximum value is 1, you multiply. Again, some points it is 0 and some point it is 1. Therefore, the integral is clearly finite valued. Okay. So e to the minus t mod of cos 2t is an exponentially decaying function in the range of 0 to infinity. Therefore, h2 of t is the impulse response of a stable system. Okay. when t goes to infinity, then it leads to e to the minus infinity, that is equal to 0. So when t tends to infinity, e to the minus t gives bounded output, and u of infinity is equal to 1. So the system always produces the bounded output for bounded input signals. So the system is stable. Let us move on to the, therefore H2 of t is a stable LTI system. Let me take the third example. The third one is, what did I give? N times cos of n pi by 4 something, right? Yes, n times cos of pi n by 4. H3 of n is equal to, now discrete time, n times cos of pi n by 4 u of n. So the condition is it is absolutely summable. So when n is equal to minus infinity to plus infinity, h of n should be less than infinity. Okay, so let's put n is equal to minus infinity to plus infinity, n times cos of pi n by 4. So this is u of n. Because of the u of n, it is one sided, so it starts from n is equal to 0 to infinity, n times cos of pi n by 4. You take magnitude, that n is coming out of that magnitude. Now what is the sequence? As n increases, this also increases inside the summation, therefore it grows, when n increases. So this sum does not have a finite value because the function k here, n here, okay, because the function n increases as the value n increases in the summation. Therefore h of n cannot be the impulse response of a stable LTI system. Its value is going to be infinity, because when n equals 0, then 1 times cos of 0, when n equals 1, 2 times cos of pi by 2 plus n equals 3. Wait a minute, I am sorry, I wrote wrongly. When n equals 0, 0. When n equals 1, 1 times cos of pi by 4. When n equals 2, 2 times cos of 2 pi by 4. When n equals 3, 3 times cos of 3 pi by 4, plus and so on. Every time this is going to give some non-zero values, right? Cos of pi by 4, 2 pi by 4, 3 pi by 4. Sometimes it may give 0 also. When it becomes cos pi by 2, then it becomes 0. Anyway, majority of the terms are non-zero terms. So if you add all the terms, infinite number of terms you are adding. In the summation, infinite number of terms are added. Non-zero terms, infinite number of non-zero terms. So finally it shoots up to infinity. Therefore the end result is going to be infinity. Hence this H3 of n is the how can I say, H3 of n cannot be the impulse response. It can be an impulse response of unstable system, but it cannot be the impulse response of a stable LTI system. Okay, so that's it. Let me stop at this point.